then we played with some real wires, some real batteries, and then moving over to our Heath Kids, the company that made that little box, we played with real power supply or voltage supply or voltage source. We played with real resistors and then real photocells and real low light emitting diodes. Lots and lots of individual components. What I want to do today was take that experience, which was admittedly, hey guys, here's a million new things, let's see them. Okay, see you later, bye. It was a really, really fast pace. What I'd like to do is sort of digest what we saw, because there's lots and lots of particular little tiny details that over time, by the time we're done with our electronics unit, probably closer to spring break, which is very soon, the end of this month, spring break. Gosh, it's almost the end of February. Working with these electronic components will literally be second nature. It'll be like, oh my gosh, it's a computer, what do I do? What's this thing over here with the button? It's a mouse. Of course you know what a computer is because you know what it is. You know what the keyboard is, and if you're familiar with the operating system you're using, no problem. So that's the same with all technology that may look goofy and complex, and I have no idea what I'm doing when you first start. After you do it for a little bit, it just becomes second nature, and then off you go. So one of the things we started out with inside our lab on Monday was using our multimeter, in which we had a copy of one of these guys, and the multimeter allowed us to measure aspects or measure features of real devices because we can't see it with our eyes. So the balloon thing, my balloon's over there, but you guys understand, I blow the balloon up. We can tell with our eyes if the balloon has air in it, it's filled with air, or it's not. You can just tell because that's a measurement we use with our eyes. In this case, we can't really tell if the battery is filled with high-pressure electrons or not until we test it somehow. We either have to measure with this device or we plug it into a little circuit that should be working. And if it doesn't work, even after you plug it in, of course you guys have been through this, maybe the battery is dead. If you don't have one of these testers at home, maybe that's a dead battery. You put a fresh battery in, still doesn't work. Now you have to troubleshoot the device. But in the electronics lab, we have this little guy right here. And what I want to do is sort of through the magic of making sure this screen is up. I just want to double check. I had a little bit of coffee this morning. The screen really is up, right? This is the board.
Yeah. Because
these are permanent markers. And every time somebody writes on the real screen with a permanent marker, an angel loses their wings, and I think I get fired. So I want to make sure this is up. So this is kind of cool because what it does is it projects that little battery I have over there underneath the projector over there, and we can draw on it and talk about things without actually having to have a PowerPoint up. It's just an image of a very large battery, and I don't have to draw it. So we already know by using our eyes, this is a AA battery. That is its name. It's its nickname. You guys have seen C-size batteries, and you've seen D-cell batteries, and you probably have seen AAA cell. They even sell as quadruple A. They're really tiny. What happens is the size of these batteries pretty much dictates how much electrons. They're a larger container. I mean, it really is the case that a D cell will typically last longer and supply more current and more actual electrons than a C cell because it's physically smaller. Same thing with a AA, a AAA, and even have quadruple A's. But they all have about the same voltage. They have the same push. It just depends on how big they are. So if I were to rotate this guy and go over and again looking for a value of what's actually in there, this guy does say on the side of it, right there in very small letters, written vertical, it's very hard to see. It says 1.5 volts. Okay, so we know just because we use them, and of course we could use that to measure it. In the lecture, when we talk about a battery, we go ahead and we say rather than drawing a facsimile of that, we draw one sort of plate, call that positive. We call a second plate, call that negative, and then we sort of have two wires off of it. That's the international hieroglyphic for a battery. Okay? If we happen to have two batteries that are stacked, okay, now I don't need to do this too artfully, of course, but if I happen to have two batteries that are stacked, maybe you'll see that inside a remote control where you need to put two batteries into it. I think the batteries are side to side, one upside down, one right side up. But whenever we stack batteries like that, the negatives on the bottom, and then there's the plus, and the plus talks to the negative, and the negative talks to the plus. Okay? So it's not as if this negative and this plus will short out. It's like saying, and I didn't bring my my meter stick along with me, the height from the floor to the table is this high, and if I grab another table and stack it on top, then I just doubled the height. And that's how voltage works. Okay? Even though this says it's negative, when I touch it to the positive, it just keeps on upping the voltage. So it turns out, if I were to draw this guy here would give us 1.5 volts, as if it was very much similar to a meter stick or a yardstick. This is 0 down here, and then this distance is 1.5 volts, so that's 1.5 volts there. And then this guy, we're told, is also 1.5 volts. So we add it, and then so up here we get 3.0 volts. So those TV remotes, those Wii remotes, any little tiny device that uses 2 AA batteries requires 3 volts for it to work. But instead of buying a 3-volt battery, it's more convenient to put 2 1.5-volt batteries in. That's just the way it works. There are some devices that take 4 AA's, and there's some devices that take 6 AA's. You keep on just stacking them. So because this 1.5 volts is really only talking about a difference between here and there. Remember our big old triangle from last semester? So difference. Capital D, delta in Greek. That's what the delta stands for. It's not a triangle. It looks like a triangle. It's actually the capital D for delta. We've already seen capital sigma for some. That's an S. This is the Greek version for S for some. This is the capital D for delta. So this guy is actually a difference of 1.5 volts, and this guy is also a difference from 1.5 volts. Since the battery is only telling you the difference between the 2 poles, it does matter where you're measuring from. Okay? If I were to take another battery and put it down here, okay, next to it, these guys aren't connected electronically, but it would be as if I'm starting another stack of volts over here. This is down here, this is there, this is a difference of 1.5 volts. Here's the 0 down here, so this guy is 0, this is delta 1.5 volts, okay, up to there. Just like, for those of you who were with us last semester, whenever we were drawing a picture, we needed to say where 0 was. We needed to put some sort of graph. So, opening this red one in a second. We said, inside our pictures, we're going to have 2 axes. One guy is going to be X, and this is the plus X direction, and one guy is going to be Y, and that's the plus Y direction. And let's call 0 there. We need a common place that we're going to call 0. And then we'll measure where we are from there. So if I were to say how high is this desk, what would you estimate? You can use feet or meters. You know, it'd be cool to use meters. How tall is this desk?
3 feet.
3 feet? I like feet too, okay? Now, of course, that's the answer I was looking for. It was the answer I expected. If you were a total smartass, you would have added the fact that we're on the 3rd floor of Holroyd, right? And if I asked, how high, what's the sea level? How high above sea level is this desk? Right? No? Yes? What I would do is I'd go out somewhere on campus, there's a little tiny plate in the ground that says how many feet elevation this place is. The building is itself, then you would add that many feet to here. So above, it all depends on where you're at. So sea level is some weird little thing where they go ahead and take the average level of the oceans, and they call that sea level. And then we can measure how high something is, how much above something is by sea level, or how much below something is by sea level. We need a reference. Same thing with this 0 for the batteries. This guy is the negative terminal of this battery. That's the positive terminal. The battery's saying that it's a difference of 1.5 volts. This guy's also saying it's a difference of 1.5 volts. But it depends on where the reference is. This guy is 1.5 volts above 0, as I've drawn it, and this is 1.5 volts above 1.5, which makes it 3. So we need a reference. So just like height and gravity calculations ultimately use sea level as a reference, we need a reference for where 0 is, and we're going to call that ground. Just like the ground out there. So how high is this desk above the ground here at Holroyd? We literally go outside and measure down to the ground how high it is. Why is it called ground? Let me get over here so I'm not doing that guy. Here is the earth. Fantastic. Here is a happy little tree. Wonderful. I feel like Bob Ross. A happy little tree. There are electrons everywhere. Okay, I see dead people. There's electrons everywhere. Where do we find electrons? If you had a point, I've hidden some electrons in this room. Where would you find electrons? That what? Where are you pointing to? The lights. The lights electrons. Any electrons in this room? Projectiles. Yeah, slide that. You're on this slide. The batteries. They're over here. It's a picture of them, right? Electrons. Any other electrons in the room? I'm sorry. Cell phones.
Power outlets.
I'm sorry. The power outlets. And those are fantastic answers. Then the next question is, what is the desk made out of? Before I answer, what are my shoes made out of? What is my shirt made out of? What's my eyeball made out of? What's my hair made out of? It's made out of stuff. It's made out of atoms. What are atoms made out of? Stuff. Smaller stuff, right? So yeah, we're on the chemistry floor, and we can go ahead and say, well, I study chemistry. Protons, neutrons, and ding, 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 electrons. So the question is, where are electrons? Everywhere. Okay, even the air we're swimming in has electrons. Every atom that's a neutral atom has a little tiny nucleus, and it has some electrons flying around it. It depends on which atom it is. And it turns out that those electrons that are flying around that my goofy little squiggle of an atom, it doesn't take much to scrape those electrons away. Just like if you have a board, don't you? Don't you board around? Do you ever fall off? I don't wish you to fall off.
I do.
If you ever hit the ground, what happens when you hit the ground?
You get hurt.
You get hurt. Okay. So if you're on a board and you fall down, you get a little road rash, right? You get scraped. It scrapes your skin off. So it turns out when you scrape the skin off of it, because remember, here's the people. Hi, smiling. A people has skin on the outside, and if you scrape a people, their skin comes off. No, I'm not kidding. I don't want to do a Dexter monologue, okay? If you scrape a people, and that's why people have flaky skin. Ew. In fact, your skin's actually designed to do just that. That's why you have a dead skin on top. So if you bump something, you get that little tiny. You get that little tiny dry skin thing happen. It's by design that your old skin flakes out. It's sort of like we grow a new suit of armor every few days. And the healthy skin, so everybody's going to scratch their stuff. That's dead skin. So every time you do this, off comes the dead skin. Same thing with regular old atoms. Every time I do this, okay, I've just scraped off dead skin on my fingers, but I've also scraped off some electrons. Okay, they're easy to scrape off. You would think that they're held really, really tight, like metal balls. They're not. They come off pretty easily. And it turns out, while the air is sort of just blowing, I can do a little picture of them. Isn't that what the north wind looks like? A cloud. Is that a nose? Sure. Yes. That's fantastic. Blowing. Okay. Just the wind blowing across the trees and the leaves and the ground will blow electrons, will scrape electrons off. Okay, so what happens is, when this happens a lot and you have a lot of wind, you get these huge monster clouds that have come from the west, usually. They are filled with extra electrons. Okay? They're just this, I'm not saying they're a battery, but they're a battery. Okay? They're this huge pod of electrons. Why are they high pressure? Probably because they're starting to get upset. There's so many negatives together, and they're starting to repel. After a while, the electrons, the extra electrons that the air and the clouds have picked up from scraping the earth and the people in the trees, it's too full, it has to go back where it came from. That's the ground, okay? Typically what happens is the resistance between the cloud and the ground is extremely high. Air itself is not a very good conductor of electricity. However, water is. Water is a fantastic, especially dirty water and dirty air, pollution, all that stuff. So what happens is, if you add water to this situation, this resistance goes amazingly down. Almost so much down that it's pretty much just a regular old wire. And if you connect a high pressure battery of electrons with a wire to the ground, it's going to flow. It's going to short circuit. Now, we don't actually see wires running down here. We see the little Harry Potter thing happening, right? Maybe that's Shazam. Okay? Sort of jaggy. The wire is not very pretty. The lightning bolts is the electrons from the clouds coming back down to the ground. Okay? You don't want to be there when it happens. How can we make the air more conductive? We can make it wet. So usually this is accompanied by raindrops, a lot of water. So what happens is the water that's sort of in the air as it's raining. I think thunderstorm was one of our systems the other day. As the rain is coming down, the electrons that are now stored in this giant thundercloud, they come back down to the ground. Okay. So even taking this battery, another battery. How many batteries do I have? Here's another one. Even taking this battery and scraping it on things like my shirt or this desk or my shoe, it will pick up electrons. We typically call that static electricity. Anybody have any younger brothers and sisters who do this on the carpet all the time? So when you're doing this, you're intentionally, especially if you're wearing socks, I think, maybe some special, maybe your Sunday school shoes usually do that too. When you do this over carpet, you literally scrape off the electrons off the carpet, and you start to charge up. And it's like, come here. And then when you get really, really close, and of course they're already wet because they're sweating profusely because they're afraid of you, when you touch them, it shocks because electrons jump back over. Where the electrons go, they go from you, who has this big charged electrons, through them back down to the ground. Okay? So just like sea level is considered a neutral height that everybody can agree on, that's how much height is height around the world. This ground is exactly that. We call this electrical ground. And specifically, if we're talking about the potential of the dirt, I mean literally the soil, we call this earth ground. Okay? So we literally take a wire and put it in the dirt and say, this is the potential of the earth. And any other place that has more electrons than the earth, then it will be delta voltage up. And any place around here that has less electrons than the earth, on average, not in total, obviously, it's going to be negative or below that. So we call that earth ground. The way this works is this building, Holroyd, I'm going to remove my tree. Here we come along. We get a big axe. We cut down this entire forest, and we build Holroyd. It's lovely. Okay, this giant school building, and to make sure that everything that we plug in. Notice these guys up here. Here's a plug for electricity. Depends on how you want to do it. Sometimes they're upside down. Sometimes they're right side up. Like that, like that, like that, like that, and like this, and like that, and that, and that. Sometimes they're happy faces, and sometimes they're upside down faces. You have those three plugs. This center plug, like this guy down here, this plug right here is called ground. And usually we go ahead and we abbreviate it ground. And what happens is every building, Holroyd is one of them. I think it's actually on this corner, the dumpsters out there. There is literally a piece of copper, I think it's about 6 or 7 feet long, that has been pounded into the ground with a sledgehammer, and there's a wire attaching it, and then every one of these little tiny holes is attached to it. Okay? So it turns out that if you want to know what the potential of the Earth is, how much electrons the Earth has, you can just go ahead and don't do it with your fingers. We shouldn't play with outlets. That's what this guy is. That's called earth ground. Okay? So what that allows us to do
is it allows us to compare all these things and be able to say, hey, they're above or below the earth ground. So that's what we use. Inside the lab, we had POS, we had NEG, and then we had GND. And each of these guys had 4 little holes or 4 little ports. I'm going to draw it fantastically. Okay. The ground inside that little box that we had, it had a plug you plugged in. That plug had 3 prongs. And one of those prongs connected to the central ground, and that's what this guy is. So we connected our system to the GND or the ground. We were talking about the earth ground. Okay? Picture of a battery is a large horizontal line indicating positive, a small horizontal line indicating negative, and the battery can be sideways, it can be vertical. It turns out that GND inside electronics looks like this. Depends on how many lines you want. Anybody guess what that hieroglyphic is? A bunch of lines that sort of go like this. What's that supposed to be a picture of? It's ground. It's ground, but what do you think it's trying to intimate?
Out of the layers. Ground.
It's supposed to be that, or it's like drilled into the ground, or it's a stake in the ground. It's supposed to be in the ground. So that's the idea. It's supposed to let you know that this is literally somewhere close to you has been buried in the dirt. So if we see a picture where we see this thing, it means ground. So we've been using ground inside the lab as our reference rather than using positive and negative like the positive and negative of a battery. So what we could say is if we were using batteries, we would attach these guys to GND, that's one way to say it, or we would say this is the picture of this guy. That's actually pretty nice. Hieroglyphic for ground. Why we have ground and what it's for. Okay? Yes, sir? For you? Was the song for you? Was that your entrance music? It's fantastic. Alright, that's why our electronics system inside the lab has that GND. Okay?
Are there fuses between the electrical outputs and this ground copper?
Yes, there are. The fuses are usually there to protect whatever is running through it. So yeah, and that's also isolated from
So the
lightning strikes too.
Okay, so that's more why the copper thing is there because of lightning strikes.
Yeah, exactly. And plus the building itself literally does need a true reference, but for both. But we all, in addition to being the ground for the building, we also have a lightning rod on top that goes down to that copper spike. Yeah. Of course, what Fabian is saying is that if this giant cloud comes over and it would love to dump its electrons, it turns out that, as you guys know, the longer the distance to the ground, the more resistance there is. The shorter the resistance to the ground, the smaller the resistance, and the more likely the lightning will happen. So if you are a very tall person, or if you are a tree, or especially if you're a building, then all the electrons have to do is just go from there to there. It's a much shorter distance. So what typically we'll do, I think Ben Franklin and somebody had to, they'll take a rod and put it up here and then run this wire the whole way down to this ground. So it turns out that the roof of Holroyd is now the same potential as the ground, and according to the thunderstorm, it's invisible. It can't see it. So it's just going along, again, giving the clouds a brain. Boy, I'd love to unload all those electrons. Where am I need to find a really short distance to spark. And as soon as I find anything that's closer than the ground, I'm going to unload. As it hovers over Holroyd, it won't see Holroyd, because all we'll see is that metal conductive post, our lightning rod, and it happens to be the same potential as the ground. It's as if the building is invisible. It will probably get struck because it's metal and it's conductive, that it will protect the building rather than having lightning strike short circuit on the roof, which is usually made out of rubber, and catch it on fire. And that's why when trees get stuck, they catch on fire, because the trees are wet. They're not made of metal, obviously. You don't want this to happen, but if there's a tree next to it, then we're going to cut the other tree down. If there's another tree next to it and all these leaves are wet, it's not a very long distance for the clouds to unload the electricity. They'll strike the tree, and the tree will catch on fire. That's what happens. Not bad. So, ground's taken care of. This guy, remember this white thing from lab? Remember what it's called?
Breadboard.
The breadboard. Okay. I don't need bread very often, but I think that's where it comes from. So cooks, chefs. Did I say cook? I apologize to all the chefs in the room. The chefs, they prepare their meals on a breadboard or a cutting board. That's apparently what this is supposed to be analogous to. This is where the chefs who are cooking up the electronic circuit do their work. We saw, it's a real picture, it's over there underneath the camera. Now I can draw on it over here. One of the things we did in lab was to determine how these holes are connected, and we found out by using our continuity meter, if you guys recall, we switch this guy over to continuity and then push it here. Whenever there is very little or near zero resistance between these two wires, we get the beat. So we went ahead and we used wires to find out when we get the beat, and we found out by looking at this that these guys, in fact this whole thing, the whole top row is connected to one wire. The whole second row is connected to one wire. Okay, why is that convenient? Because typically what happens is, if I'm still using batteries, we'll connect one wire there and one wire there, so that we always have a place to go ahead and grab the high voltage, the plus voltage, and the ground, not in the case of the battery, but the low voltage. What's different, of course, are these guys down here, and by pumping and probing here, we were able to find out that these guys are connected vertically. These guys are connected vertically, okay? But they're not connected to each other. This little tiny plastic little tray here sort of reminds you that they're not connected. But if you were to put something inside this hole, then these other holes next to it in the same little bump here, they would all be the same potential. They'd all be the same connection. So again, that's how you take two wires, and rather than twisting them together like a twisty tie, which sort of mangles them, there's nothing wrong with doing that. If you're doing something like an automotive, you might go ahead and put those things together and get a wire nut, or maybe take some electrical tape, twist it, and tie it down. You want to keep it that way. But for our purposes, we're going to be putting things together and taking them back apart because we're experimenting them. All we have to do is plug the wire into one hole, and if we want them to connect, we just plug it into another hole that's in the same region. Each of these breadboards has, remember they're not connected, has 1, 2, 3, 4, 5, has 5 Phillips head screws in the back. You can take them apart, and if we took them apart, we would see a little copper, little tiny band right here that it's almost like a big chip clip. And what happens is when you take the wire, I'll use this as a wire, and you put it in the chip clip, it sort of holds it. And if you look like everybody know what a chip clip is for a big bag of chips? It's really, really long, like a hair clip or a banana clip. What happens is that the chip clip or the banana clip is very, very long. So what you do is you just put these wires in the same clip, and then they're all connected to each other. So it's as if there's a chip clip, okay, underneath each of these guys. The reason why we did it this way is we tested, if this guy is our breadboard, we tested it, the input, and tested the output to sort of figure out what goes on inside the box without literally killing it and then dissecting it. There's nothing wrong. There's nothing wrong with killing it and dissecting it. Don't want to say that too loud. Especially bugs or squishy spiders, that's fine. But you wouldn't want to do that with a very young, very happy puppy named Skipper. Okay? You wouldn't want to kill it and dissect it. They're too cute. So you would like to somehow observe the behavior or the function or the inputs and outputs of little puppy Skipper without having to take him apart. That's what this analogy is. Okay, and we're going to be doing a lot of that this semester. We're going to sort of figure out how something works on the inside without literally dissecting it. Unfortunately for science, at some point, if it's new and you want to test a theory or figure something out, typically we need to go in and dissect it. Usually we do an autopsy after someone has expired, little puppy skipper or somebody else. We can go ahead and do an autopsy on them, or we can go ahead and find another system that's close to that, like an experimental something. But even when we do an autopsy or remove something electronically, we take it apart and see what goes on inside. As long as it's working and still with us, then we can go ahead and figure out how it works by just seeing how the inputs and the outputs work. So then we're going to use this breadboard. These guys are all connected to each other going up and down. Same thing down here, but they're not connected across the middle. And then if we want to, we can have a nice power supply along the top. So I just walked away with that. Here it is. So let's bring this guy down. Fabulous. Super. I think it's almost in focus. All right. Not a very convincing circuit, not yet. So what I can do is I can take another wire and run it over here to POS. I'm sorry. I even spent time to get the red marker, and then I didn't use it. What an idiot. Typically, we all make mistakes. Now this is really awesome. I want to put red for positive. Why not? And then over here, G and D. Okay. Now we have a circuit. I have a red wire and I have a black wire in marker that's connected to the front of that resistor and the back of that resistor. Okay. The way that we typically trace this, again, following the positive current, is that the current leaves POS, the positive, flows through the wire, goes into there, goes to the chiplet, goes through this leg of the resistor, through the resistor, out the other side, and then this guy through the chiplet, goes to this wire, back to ground. Okay, that's a circuit. So here's positive and ground. This is where you consider this positive. I'm going to say this is negative because it's below this guy. Of course, that's really negative. Consider this 0 if you want, but that's our circuit. If we turn this thing on and we give the positive a voltage, I like to use 10 volts because then it's easy to do the math. So 10 volts positive, GND is going to be 0 volts because that's where the reference is. We have a circuit. This is much of a pop quiz. You guys remember from Monday? Brown, black, red. Remember what that scheme is? Red is a 2, brown is 1. 0 times 10 to the 2. 10 times 100. Sorry. Equals 1,000 ohms. Okay. I'm not asking anybody to memorize that. Just be familiar with. Oh, look all the pretty colored resistors. They all have reasons. That's 1,000 ohms. If I was to measure this resistance with my voltmeter, obviously this won't work, even if I do it for real over there, because I don't have it powered for real. If I were to measure the voltage drop between here and here, okay, typically what I'll do is I'll say, let's call this point A, and let's call this point B. I'll say, what's the V between A and B? Anybody want to hazard a guess? What's the voltage drop between A and B across that resistor? 10. You like 10? Why?
It's everything you got.
There you go. Because it's the total, right? It's the same thing as measuring VAB. If I follow these wires and don't cross any resistors, it's the same thing as measuring it over here. Okay? So it's 10 volts. So let's do a little more screen magic here. Let me erase my picture. Again, this is just to let things sink in a little bit. Oh, a different circuit. Oh crap, my resistor's backwards. It's gonna blow it up. Red wire, POS, set to 10 volts. Black wire, set to GND, which is 0 volts. Red wire to there. Black wire to there. What can we say about this configuration? Let's start. How many resistors are there in total? How many separate resistors? 2. I like that. We've already learned reserved words for how resistors can be added in the circuit. They can be added in series, one after the other, like the World Series, or they can be added in parallel, side by side. I know the answer is obvious. We're just going through the motion. Is this a series circuit or a parallel circuit?
Series.
Thank you. Fantastic. How to test it? Take your finger. Do the current test. Okay. Do the trace test. I total. I total comes out of the positive, follows the red wire, jumps down to there, comes up and over, through, and down. Comes up and over and through and down, and then comes back. It's a circuit. Okay? We have to go from the positive to the ground. That will complete the circuit. If I were to, well, first of all, what's the resistance of this resistor, and what's the resistance of this resistor? I think this is brown, black, red, and this looks like red, black, red. Anybody recall?
Red, brown.
This is 2,000 ohms. That's 1,000. Fantastic, right? So again, not memorizing it. Just these are the very common things we're going to see. You guys are so sick of 1,000 and 2,000 ohm resistors. So we can use the same one for everything rather than confuse the issue. Well, that's 3,322. Look at those pretty colors. You don't need to complicate things. We're just going to use the same one all over again. Okay? They're in series. If I were to take my voltmeter and plug it into a real circuit and call this point A and call this point C and call this point B, what's the voltage between A to C, which is the whole circuit? If I were to take my
That's 10.
A to C. Why do you say it's 10?
It's cross there.
Because it's the whole thing, right? That's usually the way it works. This is the voltage for the entire circuit, the total voltage. So the VAC equals the V total, which happens to be 10 volts, because we have it set to. Okay? So now here comes the other question that we measured in lab, and we calculated in lab. Can you tell me how we go about figuring out the voltage A to B? How do we figure that out? So if I were to find the voltage, I know the push across the entire circuit is 10 volts. How much push is there between A and B? And then how much push is there between B and C? Let's do A and B first. So okay, you're already doing it. What process would we use, since we're an input-output process class? What process would we use to figure that out? What equation would we use? How would we go about doing it?
I times the voltage. You want to find the voltage, so you have to times the resistance times the A.
So we need a nice little equation, and thankfully the nice little equation is pretty nice. First of all, again, I forget, series or parallel? Series, okay? When we have a series circuit, we have what's known as a voltage divider. It divides the voltage up. Some of it drops from here to there, and the rest of it drops from there to there. But the current itself is the same, because my finger is the current test. One finger can go through the entire circuit and do the job. I don't need two fingers and split it. So it's not a voltage, it's not a current splitter, it's a voltage splitter. So I can use the voltage divider equation. We have one of those. And it says the voltage over the resistor you're worried about equals the total voltage, the total drop, times the ratio of the resistor you're worried about over the total resistance. It's just a ratio, it's a fraction. What's the fractional relationship between here to here and the total drop, and here to here and the total drop? It's that equation. You don't need to worry about why it is, it's just it is what it is. We have most of this, right? The voltage across the, well, let's call this guy, since we saw this first, let's call this R1, and let's call this R2. So the voltage across R1 equals V total. Anybody remember what that is? You wrote it down, right? 10 volts. Good. We need the resistance across R1. Anybody know what the resistance across R1 is? 1,000 ohms. And then we need the total resistance, R total. That we don't know yet. We need an equation for the total resistance.
R1 plus R2.
Add them. That little group here says add them. Why add them? Where did you invent that, Mr. Science? It's just add your favorite thing. You good?
Well, if you're looking for the total, you have to add everything up, and then that's how you get the total.
Is that always the truth?
No, it's parallel.
So yeah, not dissing your suggestion.
Right.
Oh, by the way, we only have two options. It's either in series or it's in parallel. Because it's in series, two equations come online. One, the voltage divider, and the other series is the R total equals add up all the R's. You just add them up, okay? Just like adding the straws, okay? R total. R1, 1,000 plus 2,000. I know it sounds elementary because it is. I made it simple so that I could handle it. 3,000 ohms. Fantastic. Total, 3,000 ohms. The total drop times some fraction of the resistor we're worried about over the total drop in resistance. 1,000 over 3,000. Anybody want to simplify that for me? 0.333, 1/3. 10 times 1/3. I think we saw that in lab.
Yeah, it's 6.6.
Oh my God! Wait a minute! Whoa! What magic is this? Where the hell did you get 6.6 in?
You just,
Memory? It's all memory. Where did you get 6.66?
well, you still have that many volts left to account for, so.
3.33 volts from there to there, and we were told from there to there is 10
Use
volts.
10 minus 3.3.
So you can use the obvious shortcut and say, whoa. If we were going the whole way to 10 and we've only dropped 3.33, then the rest of the way has to be 6.66. Okay? If you don't see that, if that's not something that you're comfortable saying, well, I really didn't see that. I love equations. I want to use my equations. And for those of you who were with me last semester in physics, I love equations too, and equations will never steer you wrong. Your tools are fantastic. Just use the equation the right way. Always a great answer. The voltage across the resistor we're worried about, R2, is still the total voltage times the resistance of the resistor we're worried about, which was 2,000, over the total resistance, which is still 3,000. That's 2/3. That sounds like 0.666 equals 6.66. Okay? So there are two ways to get to the answer. Either we say we have to go the whole way, so let's just subtract it and find the missing distance, or let's do the calculation. There's nothing wrong with doing either of them. Okay. Makes sense? We're good. Are you totally bored with this yet? As soon as you're bored with it, then we can move on, because that means you understand it. You good? Fantastic. We will move on Friday. You already know what we're going to look at. A parallel circuit.
Yeah.
Yay, parallel! Fantastic. My favorite kind.
Parallel.